Hello friends, you are tuned into my YouTube channel Number Collage. This is my sincere effort to help you understand basic mechanics in a simple and easy manner. In this video, we will discuss in detail how to derive equations of motion by different methods. Let us understand what is motion. When a body changes its position at every instant of time, we say that the body is in motion. For example, here the star is in motion. You will see that the star changes its position at every instant of time. When this motion is in a straight line, we say that it is a linear motion. The star is shown here in a linear motion because it moves along a straight line. When this linear motion is in a specific direction, then we call it displacement and we denote it by S. The displacement at any instant of time is called velocity and it is denoted by V. Here, the star is being displaced and its displacement at any instant of time is called velocity. If this displacement is more at any instant of time, the velocity is more. Here, the star is being displaced and its displacement at any instant of time is more. Therefore, the speed of this star is more. If this displacement is less at any instant of time, the velocity is less. Here, the star is being displaced and its displacement at any instant of time is less. Therefore, the velocity of this star is less. The velocity at any instant of time is called acceleration and it is denoted by letter A. The velocity of this star at any instant of time is called its acceleration. If this velocity is more at any instant of time, then the acceleration is more. Here, the velocity of the star at any instant of time is more. Therefore, its acceleration is more. If this velocity is less at any instant of time, then the acceleration is less. In this case, the velocity of this star at any instant of time is less. Therefore, its acceleration is also less. Now we will discuss motion curves. For better understanding of change of pattern of displacement, velocity and acceleration with respect to time, we draw their graphs. So, the graphical representation of the displacement, velocity and acceleration with respect to time are called motion curves. Basically, there are three types of motion curves. The first is displacement time curve or ST curve. The second is velocity time curve or VT curve. And the third is acceleration time curve or AT curve. Let us study these curves one by one. Consider a point Pxy on the curve y equals fx. X-axis, y-axis, origin, the curve fx, and point Pxy. on this curve, its x coordinate and its y coordinate. Draw a tangent to this curve at pxy. So this is the tangent drawn to this curve at point pxy. The slope of this tangent at pxy is given as f dash x or dy by dx or tan theta. So slope of this tangent is dy by dx. Here theta is inclination of the tangent, that is the angle made by this tangent with the positive x-axis. First is displacement time curve or the ST curve. It is a curve with time as the abscissa, that is the x-axis, and displacement as ordinate, which is the y-axis. Fs is a displacement curve. This is the displacement curve Fs. At any instant of time t, when displacement is s, velocity v is given as the slope of the tangent. So this is the tangent at point ts at the instant of time t, which will be v velocity v equals ds by dt. So the slope of this tangent gives us velocity v, which is equal to ds by dt, that is derivative of displacement with respect to time. Second is velocity time curve or Vt curve. It is a curve with time as abscissa, that is x-axis, and velocity as ordinate, that is y-axis. Fv is a displacement curve. At any instant of time t, when the velocity is v, acceleration a is given as the slope of the tangent. This is the tangent at point t v. At the instant of time t will be a equals dv by dt, that is the slope of this tangent will be acceleration, which will be dv by dt, that is derivative of b with respect to time t. We have seen ds by dt is velocity v. It gives us ds equals v dt. Integrating both sides, we write integral ds equals integral v dt. Integral ds gives us s, which is integral v dt. Here v dt represents the elemental area under the curve. So this is the velocity curve, and v dt, this area represents the elemental area. Area under the curve v1, t1, t2, v2, which is this area, represents displacement s. So this area represents displacement s. From this graph, we conclude two things. Number one, slope of the tangent, which is this tangent, equals acceleration, which is dv by dt. So the slope of this tangent is acceleration dv by dt. And number two, area under the curve, which is this area, represents displacement s. Let's understand acceleration time or AT curve. If a body is moving with varying acceleration, its motion can be studied conveniently by drawing an AT curve. We know that dv by dt equals a. So this is the acceleration curve, that is dv by dt. dv by dt equals a gives us dv equals a dt. Integrating both sides we get integral dv equals integral a dt. Integral dv gives us v, which is integral a dt. Here a dt represents the elemental area under the curve. So this is the elemental area under the curve. Area under the curve A1, T1, T2, A2 gives us the velocity v from time T1 to T2. What happens when a body is moving with uniform velocity? Consider a body moving with uniform velocity v. This is uniform velocity curve. We know ds by dt equals v, velocity. That gives us ds equals v dt. Integrating we get integral ds equals integral v dt. Integral ds is s, which equals integral v dt. Since v is constant, integral v dt is vt. This vt curve is shown in the figure. So this is the vt curve because v is constant. Distance traveled, which is s, from the starting point, which is the origin, in time t, from origin to time t, is given by the shaded area, which is this, and this shaded area happens to be a rectangle. We will discuss equations of motion with uniform acceleration. What is uniform acceleration? Uniform acceleration of a body is the acceleration when the velocity of the body is constant. That is, the change in the velocity of the body from initial velocity u to final velocity v during equal interval of time, that is, from time t1 to time t2, is constant. So the graph of the velocity will be a straight line, or it's a linear graph. We will derive three equations of motion. The first is v equals u plus at. Second is s equals ut plus half at square. And the third one is v squared minus u square equals 2as. Here u is initial velocity of the body, v is final velocity of the body, s is the displacement during time t, that is the distance covered, and t is time in which initial velocity u changes to final velocity v. By definition, acceleration a is final velocity v minus initial velocity u upon time. That will be v minus u equals at, or the final velocity v will be u plus at. This is the first equation of motion and we name it number 1. This we can show here. final velocity. Now average velocity is initial velocity plus final velocity divided by 2, which incidentally also equal to displacement s upon time. Displacement s becomes average velocity, which is this, multiplied by time, which is this. So we write s equals u plus v by 2 multiplied by t. Here, in place of v, we will substitute u plus at from equation 1 and write in place of v u plus at. U plus u will be 2u multiplied by t, so it will be 2ut, and at multiplied by t will be at square. 2ut by 2 will be ut, and at square by 2 will be half at square. So in this way we get our second equation of motion, which is s equals ut plus half at square, and we name it 2, and we show it here. This is displacement s during time t. So we have found equations of motion of a body moving with uniform or constant acceleration like this are v equals u plus at, s equals ut plus half at square, and v squared minus u squared equals 2as. We will find these equations of motion by method of integration. We know that the body is moving with constant acceleration. So we write dv by dt equals a, that is dv equals a dt. Integrating both sides, we write integral dv equals integral a dt. Integral of 1 dv will be v, and integral of a dt will be at, because a is constant, plus c1, which is the constant of integration. By using the end conditions, we will find the value of c1. In the beginning of the motion, when t equals 0, final velocity v will be the initial velocity u. So we will substitute these two values in here. So in place of v, we will put u, and in place of t, we will put 0. So this term becomes 0, and we get c1 equals u. Now we will put the value of c1 in here and write v equals u plus at, which is our first equation of motion. Now by definition, we know that ds by dt equals v, which is u plus at. That is, ds equals u plus at, which is this, times dt, which is this. Integrating both sides, we write integral ds equals integral u plus at into dt. Integral 1 ds will be s. Integral of u will be ut, because u is constant, plus integral of at will be a times integral of t, which is t square by 2. Here acceleration a is constant, that is s equals ut plus half at square plus c2, which is the constant of integration. Now in order to find the value of c2, we will use the end conditions. Now t equals 0 in the beginning, the displacement s will be 0. So we will substitute these two values in here. So in place of s, we put 0. In place of t, here we put 0. So this term and this term becomes 0 and we get C2 equals 0. Now we will use this value of C2 in here and we write S equals ut plus half at square, which is our second equation of motion. By definition, acceleration A is dv by dt. But by chain rule, we can write dv by dt as dv by ds into ds by dt. But ds by dt is nothing but v. So we write A equals dv by ds into v. So that gives us ADS equals VdV. Integrating both sides, we write integral ADS equals integral VdV from initial velocity u to final velocity v. Integration of A will be AS because acceleration A is constant. Integration of v is v square by 2 from u to v. So it will be As equals half times v squared minus u squared. So that is v squared minus u squared equals 2As, which is our third equation of motion. So in this way, we can find equations of motion by the method of integration. We will see how to find equations of motion by velocity time or VT diagram. We are discussing motion of a body with constant acceleration. Therefore, its velocity curve will be a straight line like this, where AO is initial velocity u and BC is final velocity v, and this velocity change from u to v takes place in time interval OC, that is t. The velocity curve makes an angle theta with the horizontal. The slope of the velocity curve will be constant and it will be acceleration A, and the slope will be given by tan theta. This is the slope of the velocity curve. But tan theta is BD upon AD. But BD is V minus U. So we write V minus U and AD is OC, which is T. Now V minus U will be A into T, or V equals U plus AT, and this is our first equation of motion. Now we have seen that area under the velocity curve represents displacement of the body S. So we write S equals area under the velocity curve AB, which will be trapezium AOCB, and this is the area under the velocity curve AOCB. This area is composed of area of quadrilateral or area of rectangle AOCD plus area triangle ADB. Now area triangle AOCD is AO into OC, and area triangle ADB will be half base, which is AD, multiplied by height, which is BD. We will substitute the various values, but BD is AD tan theta. See here. So in place of BD, we will put AD tan theta. By substituting various values, we write in place of AO we put U, for OC we put T, again for AD we put T, and for AD again T tan theta, which will be S equals UT plus half AT square, and this is our second equation of motion. We have seen that area under this velocity curve represents the displacement of the body during time interval t. So displacement is area of trapezium AOCB, which is this area. Now area of trapezium is given as half sum of parallel sides, that is sum of AO and BC, multiplied by the distance between the parallel sides, which is OC. We will substitute the values. For AO we write U, for BC we write V, and for OC we write T. We know acceleration A is given as final velocity V minus initial velocity U upon time t. This gives us t equals V minus U upon A. Now we will substitute this t by V minus U upon A in this equation and write S equals half U plus V multiplied by, in place of this t we put V minus U upon A. Now U plus V multiplied by V minus U gives us V square minus U square divided by 2A, and from this we get our third equation of motion, which is V square minus U square equals 2AS. What is acceleration due to gravity? It is the acceleration caused in a body due to the force of gravity. Example of acceleration due to gravity is free fall of a body. For all practical purposes, acceleration due to gravity, which is denoted by small g, near the surface of Earth is considered to be constant. Its value is 9.81 meter per second square. Acceleration due to gravity is always directed vertically downwards towards the center of the Earth. Depending upon how the body moves, a convention is followed. If the body is moving vertically downwards, then the value of g is considered positive. So for this free fall, the value of g will be 9.81, or rather plus 9.81 meter per second square. And if the body is moving upwards, vertically upwards, then the value of g is considered as negative, that is minus 9.81 meter per second square. So like this, the body is moving upwards against the force of gravity. So in this case, the value of g is considered negative. So this is about basics of equations of motion and how to derive them by different methods. In the next video, we will discuss problems based on equations of motion. If you like this video, click the like button, share this video with your friends in college. Don't forget to subscribe my channel to get more videos of this type. Thanks for watching. See you in the next video. Until then, keep watching Number Collage. Thank you.